It's recording everything.
Hello.
Okay, hey, guys, stop it. So, when we talk about the interior of the Earth, there's four main layers of the Earth. Miranda, what are those four layers?
The inner core, the outer core, the mantle, the crust.
Crust. Nice. Yeah. Are you nervous because it's recording?
No.
Okay. So, out of those layers, which one's the smallest? The crust. It's really tiny. It's like a little tiny thing. So we're not going to worry about that as we put this diagram together. Okay? What we're going to do is we're going to look at the inner core, outer core, and then the mantle, and look at how P waves and S waves progress through those layers. So down here, go ahead and write this in. You got density going on. We're going to look at how seismic waves are influenced as density increases as you get closer to the center of the Earth. So over here, go ahead and put seismic wave velocity. If you can, you can fit it in the box. That's what the box is there for, but it's hard for me to write. Then each one of these sections here represents different layers of the Earth. This one's going to be the mantle. You got the outer core and the inner core. Ta-da! So let's start off with an S wave. No, let's do a P wave. We'll do P wave. So I'm going to put a dot on here representing the first data point. It doesn't really, like, numbers don't really matter with this. We're just kind of looking at in general terms. So as the S wave travels through the mantle, guys, is it going to increase in velocity or decrease? Increase. All right. Think back to what we talked about before with the koosh. When molecules are closer together, it's easier for the wave to be transmitted. So a weird thing happens as you get closer to the outer core. Right before the outer core, the speed actually drops a little bit. Then throughout the outer core, it speeds up some more. And then it speeds up even more as it gets into the inner core. So as you progress from mantle to outer core to inner core, the velocity increases. That is the P wave. And just so this is clear to you, as density increases, so as density increases, velocity increases. Velocity. Huh?
I said pressure.
You didn't need pressure, did you?
I mean, doesn't that happen?
It does, well, but the graph doesn't show that.
Oh.
What does the graph show?
Velocity.
Oh, yeah. So as density increases, velocity increases. And that's one way that scientists, so like, where I'm headed with this, guys, like earlier we started the question out, a while ago, we started this whole section saying, well, how do we know what we know about the interior of the Earth? Well, one thing we know is that as you go down, density increases. And you can learn that just by looking at this P wave. The P wave increases in velocity. The only way it can do that is if density increases. All right, S wave. Where should I put the dot for the S wave, do you think? Where should I start, above or below the P wave?
Below.
Below. It's slower. Secondary. So it's going to increase, and then right at the outer core, something strange and bizarre happens. It goes down, and that's it. It stops. Weird. What do you guys think? Why is it doing that? Why not? It's too powerful. S waves are pretty powerful. I wouldn't want to mess around with an S wave. Dark alley. Well, it's because you're an animal. You're a beast, man. Look at it. You're totally jacked up.
Yeah.
So, any other ideas? Oh, there's plenty. So, what do you guys know about the outer core? Do you know anything that's unique about the outer core compared to the other layers?
Oh, it's liquid.
It's a liquid.
Yeah.
It's a liquid. So, what do you guys think? Can S waves travel through liquids?
No.
No. Okay. Write that down. So, the S wave is absorbed by liquid outer core. So the S wave is absorbed by the liquid outer core. Now I kind of taught this to you a little bit differently, but scientists, when they were initially examining earthquake data, they knew this about S waves. They're kind of like, wait, we know S waves can't go through liquids. Whoa! S wave can't go through the interior of the Earth, or at least it can't get through this part of the Earth right here. So it's that S wave that taught scientists part of the Earth's interior is a liquid. What questions do you guys have on this? Bring it up. Yo.
Which wave is more powerful?
When you say powerful, what do you mean by
Well,
that?
the earthquakes, right?
Causes the most destruction?
Yeah.
S wave does. A lot of it, though, is because of the orientation of the S wave. The S wave sways back and forth like this, and it just really creates a lot of stress on the crust, but then also on man-made objects like buildings and stuff.
And what does the P wave do?
P wave is compressional. It squeezes, so like it makes an electric go like that, back and forth. But this whipping motion is really pretty rough. You ever seen like little dogs? When they like attack something, they go like this. They put it in their mouth and go. Rah, rah, rah.
Yeah.
Yeah. Like what they're doing is they're trying to snap and neck up like whatever they're trying to kill. That back and forth motion is pretty rough. If the dog just went up to like an animal and started headbutting it, like, they really wouldn't do as much. Back and forth. Tommy?
When do they like end? I mean, they don't just like go forever, right? They just stop somehow.
Yeah,
They just eventually just like stop.
they do. So if you think about this, and it actually shows us a little bit better down here, and this is kind of a good lead-in to what you're asking. I mean, if you look here, you can see the waves. They, like eventually, they're going to reach the other side of the Earth, and they stop. Because there's no medium there. Medium means like stuff to make it keep going. Last one, Christian.
Are these waves made by earthquakes?
Yes, that's why we call them seismic waves. That's the whole idea. Remember, because how is it that we know about the interior of the Earth? Yeah, earthquakes. Seismic waves. All right. Anyway, let's look at this diagram here, guys. So there's an earthquake here at the X. What's that called? Like the place where the earthquake happens? Okay, I'll just tell you. Epicenter. You guys ever heard that? Yeah. So go ahead and label that. This is the epicenter. So once the earthquake happens, you can see that there are waves going out in all directions. What do you guys think this wiggly line here means? That's the S wave. How do you know that? Yeah, it's wiggly and it says it over here. And then the other one's the P wave. Hang on. I got a chunk here I gotta do. Again, these waves can tell you something about the interior of the Earth. So let me kind of section these off into different regions. If you look here, you can see like these little stick figures. They kind of have like these little waves above their heads. That means that they're detecting certain waves. Which waves did these guys experience? Yeah, they're getting both, which makes sense. Then there's this area. Go ahead and break these up like I am, guys. What I'm trying to do is group certain regions together. This one I'm not going to talk about the shadow zone yet, but I do want to talk about this region down here. Okay. In this area, only P waves are felt. How come?
Because on the opposite side of the earth, they're through the outer core.
Yeah, what happens to S waves?
It's
They get stopped. They get absorbed by that outer core, the liquid outer core. So there's only P waves because the S waves are absorbed by the liquid outer core. So that makes sense. Usually students look at that, they're going to like, yeah. How about over here? There's no P waves, no S waves. There's nothing. Why? It's mysterious and strange to me. Liam?
Because the S wave gets absorbed by the outer core,
Yep.
and the P wave, it doesn't look like it can curve. So it can't, like, go to the shadow zone and go straight.
Yeah, actually it is curving. See how like it really bends a lot right there?
can't curve that much.
But like, how come it's curving or bending away from that area?
Is it in the shadow zone?
No, like see that, like this area right here. So like from here to here, there's
Okay. Yeah.
there's no wave touching that. I mean, like once you get there, there's like right there, there's a wave, but from here to here, there's no wave. I mean, see how like this wave is curving around it?
Yeah, I get it.
Any idea why? Read the diagram. It's a little arrow. What does it say?
P waves are refracted at core.
Yeah, what does that mean, refracted? No, reflected means reflected. Refracted is something different. You ever done the thing like where you put it like a pencil in water and it like, looks crooked?
Oh, yeah.
Yeah! That one looks crooked. So it's refracted.
Yeah. Okay.
Refracted just means like the wave is being bent away. So you can see right here like the wave is being bent away from the away from the shadow zone.
Because of the liquid, right?
Yeah.
Oh, okay.
Anytime you have like a wave and it encounters a difference in density, it's going to bend.
Gotcha.
All right. So there are no waves because the S waves are absorbed. And again, they're absorbed by the liquid outer core. And the P waves are refracted. And the reason they're refracted is because there's a sudden change in density. Now, just to make sure this is clear, guys, like these zones or regions here, like the shadow zone, is the shadow zone always on this part of the Earth?
No.
No. What's going to determine where the shadow zone is going to pop
The
up?
spot of the earthquake.
Yeah, wherever the earthquake is. It will always be the same geometry. So, like, the epicenter's here, like a certain amount of degrees away, you're always going to have the shadow zone there. And the same with, like, this area here where you only have P waves. Question, Chad? Tommy?
So at an epicenter, there's S and P waves.
Yes.
And
That's all you got? Okay. It was pretty good, though, what you had there. Liam?
Alright, so if there's a guy right on the epicenter,
Yeah.
he's going to get hit the hardest compared to the guy away from it?
Yeah. The strength of the waves weakens the further away.
Okay.
Other questions? Caitlin?
Do you feel it at all when it's like on epicenter? Do you feel it at all?
It would be hard to. You have to have like instruments. You know what the instrument's called that detects them? It's a seismograph. Wait, did you say barometer? Okay. I hope not, because that would be absolutely embarrassingly wrong.
He did.
No. All right, I'm gonna turn this thing on. Let's go to the go ahead. Go to the next page. We're almost done here. We're just gonna wrap this up. All right. Hey, what does the P wave stand for? What's the P?
Primary.
That's primary, label it. And S?
Secondary.
Secondary. Which one's faster?
Secondary. You
Primary.
said secondary.
Primary.
And then transmission, what this is talking about is what it's able to pass through. So P waves
Everything.
can pass through solids? Oops. What do you guys think?
Yeah.
Pass through solids, liquids. Can they go through gases?
No.
We don't know.
Yeah. They can. We're not going to worry about that. So that's the P waves. Secondary waves can only pass through
Solid.
solids. The particle movement, like earlier you guys were talking about the particle movement. Do you remember? What's a P wave like? Like which way the particles move? Do they go like side to side like this? Or
back and forth.
Straight.
yeah, back and forth. Or like we call that compressional. What it does is it squeezes things. Whoops. So this is compressional. And this is what we call shear. You guys have probably heard that term. What's it associated with?
Shear force.
Shear. Huh.
Sheep.
So, when you shear something, it's this back and forth motion. Are you packing up there? So, shearing means a back and forth motion. What do you guys notice about S waves and their characteristics?
They're
S. Okay? They're slower, they only go through solids, they're shear. Makes it a little bit easier. How are we doing on time? We're done! Hey, what's your homework? Nothing.
Shear force tonight.
That was close.